So last time we talked about the PCB, um, the data structure that used to record the state of the process. Okay, we call this the PCB, the process control block. Now, so I think a PCB is actually implemented as a data structure. Um, so in many actually operating system, when they actually implement the operating system using the high level language like a C language, the PCB is actually implemented as a data structure, um, or sometimes even implemented as a class. Now, the PCB contains some of the key values like a CPU state, memory information, and also the program counter. So which basically, you know, stores the memory location for the next instruction to be executed for that particular process. So PCB contains a lot of information. So let me actually go back and show these information. Yeah, so this is actually the list of information the PCB is supposed to display, you know. Um, it also shows the open files, all the files that are opened by this particular processes, and all the resources like hardware resources, software resources, and also it just point out who actually created this process. You know, they just point to this is actually the parent and the children, and how many other processes that are created by this process. So the PCB basically it's just a data structure. Okay. Now, so I basically skip the section. If you read the Zai book, I skip the sections of how the PCBs are organized and implemented. So if you're interested in, you can read the, the sections, but I actually skip the part. You know, one of the discussions about you know when people actually try to implement the PCB using different approach. One 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 actually particular statement says you try to avoid these using the linked list to implement the PCB. But I choose to skip the details of implementation. So we're gonna jump to the next topics, the operations on processes. So when the operating system is loaded into the computer system, when you press the button and you start to load the operating system, uh, so a lot of process is going to be created. Okay, so for each operating system, there is something called a process creation hierarchy. Uh, it's a hierarchical structure, basically displays how the processes are created. Uh, Now, this hierarchical structure is a dynamic structure. So it is changing because a process can be created on the run, and a process can be deleted or terminated. So for various different reasons. So these actually structure is dynamic structure. Okay. So here's the scenario. So first, when the operating system starts, a root process, okay, is created. This is called a level 0. Now, if you use the Linux operating system, you're probably gonna, you know, you probably have some kind of idea what does the hierarchical structure means. A root process is basically, you know, it's the it's the very first process that was created when operating system starts. Okay, so this root process becomes the parent of all the other operating system processes. So it's actually at the very top. Okay, so this process becomes the highest ancestor of all user processes. One of the process, root process create it gonna create certain other processes. Okay, one of the process becomes the it's the ancestor of all user process. If you create a user process, this process is gonna be created by this. So let me actually first show you the diagram. Okay. So this diagram is very similar to the Unix system. It's actually basically based on the Unix system or the Linux system, which is actually coming from the Unix system. So the first is a root process. So the root process is going to actually create a whole bunch of different processes. These are OS1, OS2, basically means all the actually operating system. And most of these processes are basically running the operating system kernel. Okay. And one particular process is called init process in the Unix or Linux hierarchical structure is called init. Okay, this is actually is the parent of all the user processes. All the user processes are going to be created by this init process. Okay, no matter how many user processes you're going to create. And then each of the user process may create, its own child processes, So then these are all the children of this user 2. And the user 3 has, you know, one child, and then this child create another children. So these actually, so the top one is level 0, and then this is level 1. Level 1 basically display all the major processes that the operating system is running. So, and then level 2 basically shows all the user processes. Level 3 shows the children of the user processes, and then the grandchildren. So this is actually basically shows the hierarchical structure. Okay. So one, so this is called init. Okay. Uh, it's the parents of all the user processes. Whenever a new user logs in, a new user process is created. So user processes basically are actually created in level 2. The main task of each user process is to communicate with the user. So like Microsoft Word, Microsoft Excel spreadsheet, um, your game actually application, um, or whether browsers, the browsers, the internet browsers, Microsoft Edge, Google Chrome. These are all the user processes. Okay. So now each user process can itself create child processes. Okay. So that's these child process becomes level 3 or level 4. Okay. So then each child process can in turn create other child processes. So level 4. So you can actually just keep doing this, you know. So now while we actually create this hierarchical structure, now this is not a statical structure, right? Because when you create a user process, for example, you create a Microsoft Word, okay, doing a homework assignment. Now, once you complete your work, and then many times people just want to delete this particular process, because if you are not using the processes, you want to delete it because it's going to take some resources. At least it's going to take some memory space, right? So you want to free them up. So you may have some kind of experience when you use the computer system. So you create more and more applications. Sometimes people just keep actually creating more browser windows. So they open the browser windows, open another one, open your Microsoft Word, PowerPoint, Excel spreadsheet, and you never delete them. Now, what happens? So the performance of your operating system going to be slower and slower. It's getting worse and worse. Why? Because more processes are actually taking up the resources, taking up the memory spaces. So now, one of the processes called a scheduler in the operating system. Scheduler basically schedules all these different processes. The scheduler going to allocate the CPU time, memory, and the scheduler going to actually allocate all these resources. Now, if you have more processes, even many of the processes you are not using, they still take resources. So this is going to slow down the other processes, or make the system less efficient. So the chances are, when you actually finish your work, you want to eliminate them. Okay, so user one Microsoft Word, you done your homework assignment, you save your work, and then you want to actually quit the application, right? So then you're going to delete that one. Okay, so this is out. Now this is another one. Okay, so now you're done, but this one creates some more processes. These are the child processes. Now if you want to delete that one, so I'm done with user 2. Now the question is, what are you going to do with these two, the child processes? What do you think?
You can like attach them to a process on like a lower, well, I guess like a lower level. So maybe you could like attach them to like init maybe, so they're not floating, where you could try to like delete them recursively.
Okay, that's one way. The reason for this is because when you create the child process, this child process has a pointer pointed to the parent, which is user 2. And also user 2 has a list which tells other people, say, I created these child processes. Now, if user 2 actually disappears, now these Edge, Skypes, these processes are going to point to something which does not exist. That's the problem, right? So yeah, so you have to somehow deal with that kind of situation. Okay, now different operating system deals with differently. Okay, now some of the operating system, so when a process destroyed, what to do with the destroyed process's children. Some operating system like Unix, okay, they make the initial process the new parent of the deleted parent. Now, so in this case, if we destroy this one, fine. I directly point this to the init. Okay. Now I change my father, you know. So the Edge and the Skype say my parent just died for whatever reason, disappeared. So I actually point to the init. Make init the new parent. Okay. That's what the Unix and the Linux, Unix and Linux do, which is fine, right? So because even though user 2 is destroyed, but the process created by user 2, they actually may still actually work have something to do. They haven't completed their task yet. That's a possibility. Okay, so that's one approach. Now the other approach, so they choose this way. When the parent process dies, now the operating system is going to destroy all the child processes. This is a so now user 2 gonna die, so I'm gonna destroy all this. Okay. This is the approach, by the other processes. So it's hard to say which approach is better or worse. It's just a different, approach. So the only thing you need to know about is, whatever the different process operating system deal with that situation, you just want to make sure that if you delete or destroy any processes, you don't cause any inconsistency. You don't cause any kind of dangling process, which is actually over there but not pointed to or being pointed by other processes. That's a nightmare. Okay, so in that case, the Unix approach is actually reassign the child process to the init process. That's fine. Now the other approach is that when this one's destroyed, and then so are the children's. Okay, which is another approach. I'm not going to say this is a better approach or worse approach. It's just a different one. Just make sure the process hierarchical structure is the one that it's a consistent one. You don't create any actually dangling one. So now the next slide basically shows what happens when a process is created. Remember, in this hierarchical structure, a process could be destroyed, and also in the meantime, a new process could be created, right? It can be the old process destroyed, a new process is created. So now when a new process is created, what happens? When a new process is created, what happens?
A PCB like for that process is created.
A PCB will be created. Always keep that in mind. Every time when a process is created, a PCB will be created. It's a process control block. This is actually the data structure that basically record the current state of the process. Okay. Now, once the PCB is created, then all the fields in the PCB should be assigned values. Okay. So based on this, so first, when a new PCB is allocated, when a new process is created, a function, typically a function called creates, is initiated, and then the PCB will be created by a create process function. This is going to allocate the new PCB. Okay. Now, it's not just the creation of the PCB, not just the creation of the data structure. Also, it can actually fill the values for each of the data, each of the parameters in the process control block. Okay, so a create process function allocates a new PCB. Okay, fills the PCB entries with initial values. Okay, whatever the initial value is. So for example, the CPU state. Okay, what is the CPU state? I'm gonna say, okay, initial state is state 0. Okay, and what is the process state? Once the new process is created, the process state could be ready state, right? Now I assume that we only talk about the 3 states, like ready, running, and blocked. Ready, running, and blocked. Now, for some other operating system, while there are more states, like a new state or terminated states, so there are more actually than 3 states, then the process state may actually include like a new state. And once it's actually the hardware's, the scheduler is ready to assign, put this process into the process queue. Okay, it's called a ready state, ready list, and then the state changes from new to ready. But now, if we assume that we only talk about the 3 basic states, then the process state is going to be ready, right? Okay, the memory, I don't know, depending on where the memory location is assigned. So I just call it memory 0. Okay. So like so once the new PCB is allocated, the field like a CPU state, memory, scheduling information, and the accounting informations are filled using the initial value supplied to the function parameters. Okay, whatever the initial value operating system feel like I should actually provide these initial values to the okay, schedule 0, accounting information. I call it account 0. So now what is account 0? Now what is schedule 0? That's the state that defined by the operating system. Okay. So now the other information, like the parent. Okay. What is the parent information? So when the process is created, and what is children? The children should be known, right? So far, this process is just created. There's no children yet. Okay. So normally the parent is going to be actually assigned to itself. Okay. Now in some actually operating system could be like init state, because init state is the parent for all user state, user actually processes. So this value for each actual field should be provided, when the process is created. And then the next thing, once the actual PCB is filled, okay, initially, and then the next thing is the scheduler function. Now, the scheduler is a particular process in the operating system that used to manage all the processes in the system. So we're going to talk about a scheduler in our next topics. Okay. So because scheduler itself is a big topic, because when the scheduler actually, there you have to define many policy, many rules for the scheduler. Scheduler is actually supposed to be responsible for allocate the resources for each processes in the system, in the computer system. So now when scheduler allocate the resources, scheduler need to know what is the rule, what is the policy. When the CPU is available at this moment, which process should I actually allocate the CPU to? Okay, so that means which process I should pick to be executed. Now, it's not easy. There's no easy answer for this, because if you have 10 processes, now once the current process finished job, which process I need to pick? Okay, That's a big question, because you have to actually set up a certain kind of a policy, certain rule. You have to make sure the scheduler is fair, okay? Also, should be efficient, right? So there are a lot of different criteria you need to talk about. So that's a big topic of the scheduler. Okay, so that's something we're going to talk about later. But at this moment, you just need to know the scheduler is a process that actually used to allocate the resources for each process. So the schedule function is called to select the process to run. Okay. Now, depending on the priorities of the two processes, the scheduler could choose to start the new actually child process P or to continue executing the parent process. Because when process is created, this process, the current process is running. Now, when process is created, the process is created by the current running process. So then a new process is created. So now this process becomes the parent of this process. Okay, so that process is running. Now in that case, the CPU has two processes to deal with: the newly created process or the current process. Remember, when you create a new process should be created by a running process. So when a running process creates a new process, what the CPU going to do? Now you have a new process to deal with, the current process or newly created process. Now, what does the scheduler going to do? Whether the scheduler going to continue to run the current process, or CPU, the scheduler going to allocate the resource to the new process, newly created process. That's something the scheduler need to decide. Depend on so basically, each process should have some kind of priority. The scheduler could choose to start a new child processes P, or to continue execution of P's parent process. These are two different approach. Depend on whether the parent process, the current process, has a higher priority than the newly created process, or the newly created process has a higher priority than the current parent process. So the scheduler gonna do different, gonna perform differently. But that's something we're gonna talk about in the next section. Okay. Now the other major operation for the process is the process destruction. Okay. So the process can be terminated by the parent process. Okay. So the parent process created a child process, and the parent process can also terminate the child process by calling a function called destroy. Now, when you call function destroy, you need to specify which process you want to destroy. Okay. Now, the operating system need to make sure only the parent process can destroy the child process. You can't. A process cannot destroy a process which is not created by this process. Okay. So this is basically saying this. Okay. So now user 3 may issue a destroy to destroy the weather process, because the weather process is a child process. Okay. But user n cannot destroy weather, because weather is not created by user n. Okay. You have to know that. Also, depending on the operating system, destroy function may also destroy all the processes descendant to prevent having orphan process. Remember, in Unix, when the destroy function is issued, okay, when the user 3 actually destroy the weather process, then also these process should be reassigned to init, right? That should be as part of the operation. Now, in other process, like a Windows operating system, when destroy actually function destroy it, they're also going to destroy everything attached to the weather. So every actually child process of weather should be destroyed. And that's actually creates some kind of cascading effect. Okay. Now, that's depend on the operating system. The operating system choose to use the cascading destroy all the child process. Some operating system just say destroy this child, but all the grandchild should be reassigned to the init. Okay. So the destroy function perform the following step. After calling destroy C on all child process, remove P, either remove these from either the ready list when P is ready, okay, or from waiting list of the resource when P is blocked. Okay, I think that destroy P. When you actually destroy this process, you have to remove this process from all the different area. Like if the process is actually in the ready list in a queue, then you have to remove it because the process has been destroyed. And also, if the process is waiting for a resource, then this process should be also removed from the waiting list for that particular resource. Okay. And also remove P from the list of children of calling process. Okay. So this should all be removed because you have to remove everything just related to that destroy the process. You cannot keep anything with it. And release all memory and other resources. Okay, close all open files and deallocate the PCB. Okay. Now you cannot simply say, oh, I destroyed this process, so I remove the PCB. You cannot do this immediately. Why? Why? Because the PCB contains some pointer pointing to some places. Now, before you destroy the PCB, you have to make sure you deallocate the object that are pointed to by this process control block, right? So otherwise, you're gonna have some kind of you create some kind of orphan objects. So these are dangling objects that were not pointed to by anybody. That's dangerous. Just like one example is like if you want to destroy the process P, and the process P is actually, has created many child process. These child process has basically pointed to its parent. Now the parent is destroyed, so you have to make sure these things are deallocated. Either you destroy the children or you reallocate the children to another process. You cannot simply wipe out all the information for that wipe out all the information of the PCB for that particular process. You cannot simply do that. You have to clean up everything before you finally delete the PCB. Any questions with this? Any? Do you have any opinion, questions?
Professor, one question.
Yes.
When we're, I guess I should ask this at the very start of the class, but when we're talking about these topics, is this universal between all operating systems, or is this just the most common implementation between, let's say, for example, Mac OS, Windows, and Linux?
That's a good question. I already mentioned that in that scenario, different operating systems are going to deal with differently. But in general, there are two different approach. One approach is that when you destroy the process, it will reallocate all the children of this process to the init. That's basically used by certain operating system, including Unix and Linux. But in Windows operating system, they choose to, when you destroy the process, you basically destroy all the children of this process. These are two general approaches. Okay, so they're different, but these are mainly two different approaches. Yes, they're different. The details are slightly different, but these are two main approaches. Okay, now when a process is destroyed, and then you're going to call the scheduler again, the scheduler going to be involved. So scheduler is very important because scheduler is the piece of operating system that organize managing all the processes. Okay, so then once everything is deallocated, the PCB is destroyed. Okay, assuming that every actually information the PCB point to have been taken care of properly, then the PCB is destroyed. So you basically wipe out everything that related to the process, and then the scheduler is called to select the next process to run. Okay, and this call must be made outside the destroy P function. Okay, to guarantee that the scheduler execute only once. Okay, so again, that's something we're going to talk about when we talk about the scheduler. Okay, this is another big topic. Now, also, the things are related to the processes are the resources. Okay. Now, all the processes are actually going to be run by the CPU. All the process is going to be stored in, the PCB of the process is going to be stored in the memory. So the process is going to use resources. So that's why a resource management is also important. So the operating system maintains a numerous resources that the process can request and release at the runtime. Okay. So for example, you have hardware resources and the software resources. Okay. So, and very similar to the process control block. So if you have a processes, you create a process 1, process 2, process 3, and then you have a process control block, right? PCB 1, PCB 2, PCB 3. And then these processes actually, during the lifetime of each of the processes, then these processes are going to actually use various different resources. So then you have a resource 1, resource 2, resource 3, resource 4. Okay. So resource 1 could be like a keyboard, pointing devices, printers. So these are all the resources, memory, CPU, even CPU is a resources. Okay, so basically now the operating system is going to keep something called a resource control block. Okay, so the resource control block is, is a data structure. Also, just like a PCB, it's a data structure. So these data structure basically represent a resources. Okay, so then you have a RCB 1, 2, RCB 3, RCB 4, and then one of the data, they actually contains a list of processes. So a process 1 may request for resource 1. So then So there's actually a link that you put the process 1 over here. So that means process 1 is requesting for resource 1, and process 2 also requests for resource 1, and then you also put the process 2 over here. Now, so if you have a multiple process requesting for the same resources, then you have to actually organize the usage of the resources. For example, process 1 request for resource 1, process 2 request for resource 1, and the process 1 request for resource 1 first, and the process 2 request for resource 1 second. Then typically you assume that the process 1 will get the resources. Now, and before process 1 finish the resources, finish using the resources, then process 2 has to wait, right? Until process 1 finish the resources 1 and free up the resource. So then process 2 can grab it. Okay. You think that's probably the case, right? In general, that's true, but not always true, because then resource control block also prioritize these different processes. Now, if process 1 grab the resource 1 first, however, process 2 has much higher priority, so then you're going to preempt and get rid of the resource 1, process 1, and then let the resource 2 grab the get rid of process 1 and then let the process 2 get the resource 1. So that's why it's very complicated things. You need a operating system to organize and manage all these. So the RCB, the resource control block, is the structure. It looks like it's much simpler than the processes. There's a resource description. Okay, so what is this resource? Contains the description of R's properties and the capabilities. Okay, and then the resource state show the current availability. Now, so in that case, the state is going to basically display whether it's a single unit resource. Okay, so in that case, the state could be available or not available, right? Now, the resource could be actually multiple units. That means even though it's like a memory, so you actually allocate to one process in the memory space, but there's still actually more resources available for more processes. So, and also the waiting list. So that's something I just mentioned here. When a process requests for R and R is currently unavailable, then the process PCB is removed from the ready list and added to R's waiting list. Now, once the process, for example, once the process P is in the waiting list for resource R. Now, what is the state of process P?
Blocked.
Blocked, right? The state of the process should be blocked, because now, so that's why, when the process P is blocked, then it will be the operating system scheduler going to remove the process P from the waiting list of the ready queue. So it will be removed from RL, the ready list. So they're not waiting for CPU anymore, because currently this process is in the waiting list for a resource. So it's in one of the waiting list, of a resource. So it's not waiting for the process. Okay. So basically, let me actually draw an overall picture for a process. Okay. Just make sure we better understand how these things actually work. Okay. Let's say a process is created. So now we have a multiple resources. Okay. Let's see. Resource 1, resource 2, resource 3, let's say. I assume that there are only 3 resources in the computer system. And now these are the operating the process. So I have a process. Okay, 1, process 2. Okay, I assume there are only 2 processes. So then there's a process actually, control block, And then that's ready list. Okay. Okay, let me create more processes. So I have a PCB3, PCB4. Okay. So once these 4 processes are created, so initially they were all in the ready state. Okay. So they're basically waiting for the CPU, waiting for actually to be executed. Now, so then one of the process 1 is allocate the CPU. So so the state changed to running. And then during the execution, process 1 just say, oh, I want to actually grab the resource 1. So the process 1 gonna actually put in the waiting list for resource 1, and the process 1 start to execute the resource. If the resource 1 is available, the process 1 gonna immediately get the resource, and then the CPU gonna pick the next one, process 2, to run, right? Okay. Now process 2 immediately also wait for resource 1. So in this case, process 1, process 2 both are in the blocked state. Okay. And once the process 1 finished the resource 1, and the process 1 say, oh, I'm still not ready, I need to actually access another resource. Well, let me see. Okay. So then process 1 finished the resource 1, so it's going to be removed from the waiting list for resource 1, and then the process 1 going to be actually put back in the ready list, in the ready queue, and the process 2 get the resource 1, right? And then process 3 is executing, and then process 3 is requesting for resource 3. Okay, then the process 4 in the ready queue. Now I assume that we allocate the the ready state is actually based on the first come first served. So then process 2 finish the resource 1, then it will be put back on the ready. So now you should realize that a process, once it's created, it's always going to be jump from the ready list or from the waiting list in the resources. So it basically going to jump back and forth among these different list. So whenever they change the state. So in the ready, whenever they are waiting for the CPU in the ready list, then they are actually their state is ready. Whenever there's in the CPU, then they are actually in the running state. And whenever they actually request for resources, any of the resources, they are in the blocked state. Okay. Now, in general, if you treat the CPU as another resource, then so when a process one is actually using the CPU, it's actually you can think about interpret this as process one is in the waiting list for the CPU resource, right? You can interpret that way. So that's basically in the running state. Wherever it's actually using the CPU, it's a running state. However, the only difference between CPU and other resources is that CPU only deal with one process. If only one process is allowed to to be in the CPU. Now these other resources allow multiple processes to wait on the waiting list. So what is the waiting list for CPU? It's actually this. So the process basically jump among these different lists. It's in the waiting list for the CPU ready list, or it's in the waiting list of different resources. And then when they jump from different actually list, they change the state from ready to running to blocked. So everywhere here is blocked. And this is actually ready. And this is running. Okay. Any questions? So whenever a process is requesting for a resource, then a resource is allocated to a process if the process has access to and able to utilize the resources. A resource is free if resource may be allocated to a requesting process. So this is how the operating system basically execute a function called a request. And this is actually request the resource function, allocate the resource R to a process P. So this can actually block the P. So P will be blocked. Okay. If R is currently allocated to another process. So that means P is blocked if P is in the waiting list of this particular resource, whether it's printer or whether it's a scanner or whether it's a other hardware device. Okay. And then release a resource. When a current running process P wishes to release a resource R, so when P finished the resources, complete the printing job, the operating system execute a release function. The release resource function allocate the resource R to next process on the waiting list. So assume that you see. Oh, sorry, not in here. It's actually the Microsoft Word document. Now, assume so when P1 is actually working on, when P3 is working on resources, any process that they're waiting for R3, these are blocked. Okay, in the blocked state. Okay. Okay, now let's talk about a scheduler. The scheduler actually going to be done using something called a scheduler function. Scheduler determines which process should run next. and it starts the process. So the scheduler is very powerful, right? It's the boss, okay, who determines who gonna actually get a chance to run and who get a chance to do the things. So the scheduler function is called at the end of each of the process and the resource management function. So now this is just actually a particular case. Just tell you how the scheduler actually works. Now we assume that the ready list is implemented as priority list. So that means it's a ready list. So you have process 1, process 2, process 3, process 4. These are in the ready list. Okay, these processes are all ready to be executed. Now, if it's actually implemented as a priority list, then it determines who has the highest priority. Okay, now if process 1 has, let's say, priority 3, process 2 has priority 2, process 3 has priority 4, and this has priority 1. Let's say, suppose priority 1 is the highest, okay, and the 4 is the lowest, okay. So then, whenever the CPU is available, the scheduler gonna say, okay, CPU is available, who is next? And the scheduler gonna look at all the processes currently in the actual ready list and find out, oh, P4 has priority 1, which is the highest. So then the scheduler gonna pick the process 4 and execute the process 4. Okay, and then next one is process 2, next one is process 1, and the process 4. Now this is actually, you know, how the scheduler actually schedule the execution of the processes if the ready list is implemented as priority list. Okay, so if that's the case, the scheduler function perform the following task: find the highest priority process queue on the RL, which is a P4, and perform a context switch from P to Q. So P is the current process in the CPU. Q is the next highest priority in the ready queue. Okay, so the context switch is going to happen. It's going to switch the current process and the process in the ready queue, ready list. So the context switch happens if either of the following conditions is met. The priority of the running process P is less than the priority Q. Okay, so now the priority in the ready list has a higher priority than the process is currently in the CPU. Then switch, context switch, because you have to I have to kick you out and replace with a process with higher priority. Now the other thing is that the state of the running process is blocked. Now the running process just decide, okay, I'm done. I'm waiting for the resources. So I'm going to actually put myself in the waiting list of particular resource. So I just block myself. And then the scheduler going to say, well, the current process decide to quit, waiting for the resources. Who is next? And then you're going to pick the next one. Okay. So that's the that's how the scheduler actually schedules the processes. And we're going to discuss this scheduler in the next chapter, in the chapter 3. Okay, we're going to talk about something called a scheduling algorithm. Okay, now the next topic in this chapter 2 is the threads. Okay, now remember, if you actually want to actually execute a program, so once you actually copy the program into your hard disk, say, okay, I buy a computer game, and I just actually copy the computer game in my hard disk, or I just download a computer game. Now, once I decide to execute play the game, I need to actually load the program into the memory. So I need to create a process. A process is created, so it's running. So then I can play the game. Wherever the CPU is available, the game is running. Now, so that's basically called the application implemented as single process, follows a single path of execution through the program. Okay, so once this is hard disk, okay, I store this program. So this is memory. Okay, so when I decide to run this program, so basically I copy the program from hard disk into memory location. Okay, so then a process is created. So then I create a PCB, process control block. And then I put this process into the ready queue, right? Ready list. So the process is in there. Once the CPU is available and this process is picked, then I start to actually run this process. Okay. Now, this is actually called a process with single threads. A process with single thread of control. So I can execute the, once the actual process grab the CPU and the CPU start to load the instruction one after another, to the CPU. CPU basically load the instruction, execute, and this is like again, it's a cycle. It's called fetch, decode, and execute. Okay, so for each instruction, it's fetch, decode, execute, and then fetch, decode, execute, fetch, decode. So it start to actually run this as a single thread of control. Okay. However, if the execution blocks, so in particular instruction says, okay, I need to wait for the IO, wait for the import, then it will block itself, waiting for some resource to become available. And in this case, the entire process blocked. So the process actually is blocked. So the CPU has to actually execute the other process. This process is a complete halt. Okay. Now, in many applications, people just find out, okay, now if I only actually have a one thread of control, then if this process is blocked, the whole thing is blocked. Okay. So the whole application is blocked. So many actually, applications, they want, the CPU going to take care of this, so they should be able to, have different parts. Okay, one part is blocked, the other part is still going to be able to run. Okay, so the independent part can run. Okay, so now in this case, you have to create a process and multiple threads. Okay, multiple threads. So for example, if I load a Microsoft Excel spreadsheet, Microsoft Excel spreadsheet is a typical example of multi-threading. So it's a one application, but has multiple thread. Okay. One of the thread is deal with the update of the cells. Okay. If you're actually familiar with Microsoft Excel spreadsheet, you're probably actually going to be able to know how these things are working. So for example, let me actually show you. Okay. Not this one. That's not the one I want to. So if I start the Microsoft, if I have a list of like A, B, C, D, E, F, or whatever. So I'm currently editing this, okay? And also I'm gonna currently do something else. So, or I just say 1, 2, okay? Okay, so now I have imported some other data, okay? Oh, sorry, not the one I want. So now, then I'm gonna create a formula. So the formula gonna actually just let's say calculate sum of these items, right? Okay. So this basically give the sum of these numbers. Now, so if I have millions of items in the Express spreadsheet, so I want to create the formula and try to add, try to calculate the sum of all these numbers in the cells. This is probably going to take a while, maybe a couple of seconds or minute, even a minute, depending on how fast the computer is. Now, in this case, I can create one thread to perform these operations, the addition of this. And then I still can actually, edit the other cells. So in this case, to calculate the formula and editing the cell could be a different thread. So even though these threads are both working on the Excel spreadsheet, but they can operate independently. That's called multi-thread. Okay. Now, so the difference between single-threaded actually process and multi-threaded process is that a single-threaded process actually has a one thread of control. Multi-threaded process has a multiple control. Another example, a good example for the multiple thread process is the web browser. Okay, the web browser. So I can create a web browser. So here's a web browser like a Microsoft Edge or Google Chrome. So I use Google Chrome most. So I create a web browser windows. Now in the web browser, so I can create a multiple windows. Okay, I can create multiple windows. So let me actually show you what I do. So so you see that I have a multiple windows. Okay, now each of this is actually each of this is actually a thread for these. So I have 1, 2, 3, 4, 5, 6. Then I can actually run each of these independently. For example, here I can just type a keyword and search for, use the Google, I search the Google, for example, I search the Google, search for something, right? And I click, and then I switch to another browser. So each browser window are basically an independent thread, even though all these browser actually window basically are running the same application, but each basically working independently. So I can actually use one browser to do the search, some particular keyword. I can use another browser to actually access the, make the purchase like on the Amazon.com. So these are actually, browser windows. These browser windows are each are independent. Okay, so that's basically the multiple thread. Now, each browser window basically run the same application, but they are different. They have a different thread of control. So this one browser actually doing the Google search. The other browser is actually doing the online purchase. So they're actually running independently. Okay, so that's a multi-thread scenario. Okay, so now what's the difference between, so then we have a process, and we have another process. One process basically running a single thread, and the other process may have multiple threads. Okay, so even though they are running the same application, but you actually open a multiple thread. Now each thread has its own independent, thread of control. But this is actually the one threaded actually things. So now, because each thread has its own independent control, then you have to create something called thread control block versus the process control block. But the thread control block is part of the PCB. So that's something. So we're going to talk about it. So we only have like a couple of slides left. So we're going to continue with the topics, but I'm almost done with chapter 2. So we're going to switch to chapter 3. Okay, next time. But I'm going to, finish the chapter 2, the thread part on Tuesday. And then we're going to start the next one. Next one is very interesting. It's the scheduler. And we're going to talk about the scheduler algorithm and how the scheduler can to manage all these different processes. Okay. So I think yes.
Sorry. I was going to say we don't have class on Tuesday because it's the wellness day. And then I think Thursday we're doing the quiz.
Okay, then we move to Thursday. It's just the next class, Okay. Thank you for pointing out. Okay, so do you have any question?